We are starting with the part A of the problem, and as the string or rope rather that is lying on a horizontal frictionless floor, you can understand that there is a force of gravity. If the mass of this rope is taken to be, say, m, we are assuming it, then there's a force of gravity acting on this rope downwards and a normal force applied upwards by the frictionless surface on which the rope rests, and during its motion there is no frictional force acting on it, so the normal force balances the gravity force, and we are not concerned about these forces because we are dealing in the horizontal motion of the rope. So let me assume that the mass of the rope is small m, and since they have given the length of the rope is capital L, we can define a term called linear mass density, that is lambda, given by mass per length. Obviously the unit of this quantity lambda is coming out to be kg per meter, and the value of m by L, that is lambda, remains constant throughout the length of the rope because the rope has been said to be uniform. The question says that is pulled at one end by a force F. So they are telling a force of F applied at one end of this rope by an agent here. And let us consider the direction to the right as my positive direction. This is my positive x direction, and as I said before, although the rope has got a force of gravity mg acting downwards on it and a normal force given upwards by the frictionless surface on which the rope moves under the force F given, we are not showing those vertical forces because the rope has got no vertical motion, and we are concerned here about the horizontal motion of the rope. We shall not show those forces in this problem. Let us assume further that the acceleration of the rope as it moves to the right under the applied force, that acceleration is a, and you'll agree that since the rope is one continuous body, its acceleration is small a, that I show here, is the same at every part of this rope. Now the question says we have to find an expression for the tension in the rope as a function of position along its length. So what we do is this: we just draw an imaginary vertical line that divides the rope into two parts of unequal length, as you can see it here. I have just drawn a vertical line in dashed line, that is, it's an imagination. We are just breaking up this rope into two parts, and suppose the right side portion has got a length of x measured from the end where the force F was applied, and since the total length of the rope was capital L, L minus x is the length of the remainder portion on the left part of that imaginary vertical line. I just insist once again, this is all in imagination. To solve the problem, I am just breaking up the string into two parts of length x and L minus x by this imaginary vertical line. You know that whenever a force F is acting on this rope, dragging it to the right, then at every single point of the rope there is a tension force acting in a pair. In the problem so far you have assumed massless strings or massless ropes, so that along the length of the rope the tension force remains the same at every single point of the rope. But here the problem is different. We are doing a question where the rope is of non-negligible mass, and since the rope has got mass, we can conclude that the tension in the rope at different points varies with position. We have to find that relationship in this question here. So suppose at the point where that vertical imaginary line breaks up the string, we have got this tension acting in a pair, and let me call that this tension force magnitude here is, suppose I call it T. To the right I call it T, and to the left there is a pair here actually acting, action reaction pair, that we call minus T, and we said that this T is a function of position x. If we take some other point at some other value of x, the value of T will also change, and that is the novelty of this problem. So this is the figure we have got. With this, let us proceed now to draw the free body diagrams of the two parts in which the rope is being broken. You understand that as the rope is being cut into two parts, the two sides of the rope, they look like this. And I'm going to draw the FBDs of these two portions, identify the forces acting on them, write equations of motion, and proceed accordingly. So first of all, I take the portion on the right side of the imaginary line and draw its free body diagram. This is the portion here of length x. So this length is x, and the force acting on these portions is of course the force F applied by the agent to the right and a tension force that is acting to the left. You might ask why it has to be to the left, why not to the right? Because I have shown here a pair of tension forces acting equal and opposite, and T and minus T. And why should you choose minus T for this smaller portion on the right? That is, we have to just understand that. So for that, let me draw the FBD of the other part, the left side part also simultaneously. So I just draw these two figures side by side for your convenience. And here the length of the left side portion of the string is L minus X. And you see that the only force that is dragging this portion to the right has to be directed to the rightwards. Because if the whole string is moving under a force of F to the right, and tension pairs being internal forces within the rope, the only external force acting on the whole rope is F. And any portion of the rope must be moving rightwards with an acceleration of A. So, considering the left side portion, the tension force out of this pair, we must choose the force T to the right because there is no other force acting on the left hand portion of the string to the rightwards. So the motion of this portion can take place towards right only if the tension force acts on it to the rightward direction. And so we say that on the left side portion, if an applied force was F to the right, the tension force, that is minus T, must have acted to the left. This is the way you must be choosing the direction of tension forces on the two parts of the string, keeping in mind you should find a logic that under what force these strings portions can move to the rightward direction. So I hope you understood why we have chosen the force of T rightwards on the left portion of the string of length L minus X and a force of minus T acting leftwards on the right portion of the string that was cut out by this imaginary line. Acceleration of both the portions shown in my figures, FBDs, must be A to the right for obvious reason because they are nothing but the two parts of the same continuous rope which I have broken down only in imagination into two parts for the sake of the problem, no further. So let us write down the equations of motion for the two portions. For the right hand side portion of the rope, that is the smaller one in my figure to the right, we could write down the equation of x motion of this portion is coming out to be sigma fx, that is the net force in the x direction. Applied force is capital F to the right, that's positive. Tension force, as you can see, it's minus T to the left. So it is F minus T in scalar notation, that is the net force acting on the portion. Now let's find out the mass of this rope. Now you have seen already that since the rope is uniform, its linear mass density lambda, mass per unit length, is coming out to be small m by L. And since the length is x, then you could write down the mass of this portion is coming out to be m into x by L. Understand the expression? I write it in bracket to let you understand carefully. M by L, length per unit length. And since the length is x, this portion's mass should have been m by L into x. That is the mass. Acceleration is taken to be a here to the right. That's my equation number 1 for the x motion of the right hand side portion of the rope. We are not writing the equations of motion in the y direction, that is vertical direction, because we know already that gravity force and normal force are equal and they don't come into our calculation. Similarly, let's proceed now to write down the equation of motion of the left hand side portion of the rope, and that is of course this portion here. So looking at the figure once again, you could write down that sigma fx, the net force acting on this portion, is the only force of tension that drags the portion to the right. This is T, the force is the mass for the portion, as you'll agree with me that m by L was the length, mass per unit length, and the length of the portion is L minus x. The thing in square bracket here is the mass of the portion that is shown here. You can easily say this, the mass inside the square bracket. Acceleration is the same as before, that is A, and that's equation number 2. We have got the two equations of motion for the two portions in which the rope has been cut into, divided into by an imaginary line shown by this vertical dashed line here. Add up these two equations. I just leave some work for you.
Hello students, you got a glimpse of our video lessons through this small lecture. We have hundreds of lectures like this one covering various topics of advanced school level and intermediate physics in our website. They are exhaustive and often accompanied by elaborate diagrams to make concepts even clearer. They are taught with passion and sometimes with a bit of fun. So, at the end of the lesson, you have a commanding grip on the subject and you are ready for the board and competitive exams. Subscribe at physicsacademyonline.com to access video lectures of highest standard on various topics of physics.